Today we're going to see how many of the 4 little experiments we can get done, and there are things that they have in common, and you will see when we get there. So there's a potassium iodide electrolysis and a sodium sulfate, and they have something in common, and there is water with sodium sulfate, and they also have something in common. And if you can kind of use that as a gauge to help yourself remember what's going on, then that will help you. So this looks like a lot of information. So we're now looking at aqueous solutions. So we're looking at salts that are dissolved in water, and there's going to be at least 2 cationic species there and 2 anions in there, and they can all be oxidized and reduced. So for each one, again, we go, you need to know the electrodes, you need to know the electrolyte, you need to have an observation for both cathode and anode, as well as the half equations, and you need to know what the spectator ions are, because that's going to help you with your cathode and anode reactions. I'm going to change how I do it ever so slightly in terms of how you're going to record it, and hopefully that will make your life easier. So I'm going to have this gentleman turned off. So this would be the setup if we were to do the electrolysis of copper sulfate with copper electrodes. So the copper sulfate, in reality, here I have to change my screen, don't I? Yes, I do. Is this one. So here in reality, this would be the bright blue liquid is what we would see. And we now have our copper anodes. And copper anodes, or our copper anode and cathode, are going to be active. They're actually going to take part in the electrolysis. So you can read along the bottom if you wish, but I'm more interested in you actually looking at what is happening inside in the vessel. So can we remember yesterday which one is oxidation, which is reduction?
Cathode is reduction.
Cathode is reduction. So which line is the cathode? The small line or the big line? Up here.
The big line.
So big line is your anode. So the small line is your cathode up here. So again, SEC will not necessarily put pluses or minus. Okay, what's the difference? What's happened in the animation from the beginning screen? I need to go back and show it to you.
Looks like the piece of copper on the left was corroded.
Okay, so the anode on the left, it's definitely smaller in size. Is there any other observation?
There is bubbles of gas.
Not necessarily. So these things aren't bubbles. These are supposed to be the ions that are in solution. So give me something else.
They're like a bit of the anode that's kind of dissolved is sitting at the bottom.
Absolutely. So this is called sludge, but yeah, you're absolutely correct. So the anode has gotten smaller, definitely. We've got this sludge at the bottom, and I'm not sure whether we can see on the right from his animation, but in reality the cathode over here will actually get physically bigger. It gets physically bigger, so you're actually putting pure copper onto your cathode side, and because you're oxidizing your copper here, you're going to be reducing it on this side. Okay, so I'm going to have to change my share again. You have this part. Okay, so in terms of you, that just disappeared, didn't it? In terms of you, we have copper sulfate in solution. What do you think my spectator ions are going to be? So what do we say the electrodes are?
The rods that...
And what are they made of? And what are they made of?
Copper.
Copper. So this is now on the top right. It's page 205 for me. What was the electrolyte? What do we say the electrolyte is?
Copper sulfate.
It is the copper sulfate. Okay, if we're now saying that copper is oxidized at the anode and reduced at the anode, or reduced at the cathode, what is the spectator ions in this? So what ion? SO4 2-. Okay, so the reason these guys aren't involved is that there isn't enough energy in the system to actually make them get involved. Okay, now you have headings written in there: diagram, equations, and blurb. I'm going to change how we do this. Remember we did this triangle thing earlier? Once upon a time, we have it's kind of, yeah, Johnson's triangle. So we're going to use that. Will this let me go backwards? It will. So in your page for me, write a triangle. I'm going to move this up so I have a whole screen to do it in. You're going to draw your triangle like this. Up the top, we're putting what we see. This down here is going to be the explain part, and over here is going to be the half equations for this. So in here, we're just going to draw ourselves a quick little diagram so that we remind ourselves. So the big line is the anode, the small line is the cathode. Okay. I'm going to change this slightly. Sorry. Okay, it doesn't look like this shape, but I'm going to make it this shape so it's really, really obvious. Okay, and we have our sludge down here. So this is my anode, big line, small line cathode. This is the copper sulfate in here. This is going to be pure copper here. These are impurities. So what were our observations? What were the observations you gave me? Tell me what happens to the anode.
Impurities fall off of it.
Okay, what else happened to the anode? I'll put that in a second, but what else happens to the anode?
Got smaller.
Yeah, so we say it loses mass. So your anode is loses mass. I think it is. It loses mass, and there is sludge at the bottom. Lads, I prefer my other sludge at bottom. What happens to the cathode?
Gains mass.
Yep. So cathode, from our observation, it will increase in mass. And we'll just put Cu in brackets. So that's what we see. So what did we say happens at the anode in terms of oxidation reduction?
It's oxidized.
Okay, so at our anode, and I'll move this up in a second. So at anode, our copper is oxidized. Can I move this up a slight bit? So copper is oxidized, and impurities lost. And at our cathode, so before we can write the cathode, can anyone give me the half equation for copper being oxidized? What would I write? Where do I put my electrons?
On the left hand side.
Would you put your first child on that now, Lucy? Think of the stupid things that I use.
Not anymore.
Not anymore, good. Okay, so remember I used the OIR. So oxidation is an increase in oxidation number, and the electrons are going to go on the right hand side. Okay, here is now a question. From this, can you tell me what is the oxidation state of the copper?
2+.
2+. Okay, so this is there's a minus here, but it won't let me write it in. So that's my half equation for the anode. Okay, that is oxidation of copper. So then at my cathode, it's this Cu2+, which is reduced. So what we've done, I'm going to change the color of my pen. What we've done here is the copper that's come here, we've actually turned it into Cu2+ ions that are now in solution. And because there is a current flowing, the positive cations will go toward the cathode. And once they go to the cathode, they'll pick up electrons and they will be reduced.
Miss?
Yeah.
Does that mean then that the anode would eventually just like only be the sludge?
Correct.
So, okay.
And the reason why you use the copper sulfate as your electrolyte is to ensure you have loads of Cu2 plus in solution for you. You could do this with water, but it would just be much slower. Okay, but you're absolutely right. Eventually the anode would disappear. Okay, so our cathode, our copper is reduced, and the cathode then half reaction. I put my electrons this time on my right hand side. Ooh. Plus 2e minus goes to Cu. Now you can put this down arrow after the Cu because that's kind of saying it's plated on. But it's not. The SEC won't mind if you don't use that as a half equation. Okay, are we happy with that one? Are there any questions? Okay. So we've just done that. We've 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 done that. Okay, so the next one we're going to go is the junior cycle one, the Hoffman voltameter. I think you're the last junior cycle people. So I need to change my share. New share. This one. Okay, so this is a homemade version of it. So can you remember this? Did you do it with the little tiny Hoffmans, or did you do it with the big giant one? You remember? Don't remember, don't care. Okay, so what the Hoffman voltameter is, it's essentially like two funky burettes, but they're linked together. And you would have your electrodes down at the bottom, and you have a little tap up the top because you want to tap the gas off, and essentially you are electrocuting water, for an easy way to describe it, and you're breaking water up into its constituent molecules. So she's on your leads eventually, and if you leave it for long enough, you will see production of a gas, and one of them will have twice as much gas than the other. Can you figure out why one of them has twice as much gas as the other?
2 hydrogen, 1 oxygen.
Yeah, that's exactly it. So you make twice as much hydrogen as you do oxygen. Okay. So it's really easy to figure out why the anode is oxygen, because it's been formed by it being oxidized. Okay, so we go back to here. Okay, so we now have, this is a slightly more difficult one to figure out in terms of cathode and anode reactions, but we're going to try. So my electrodes here are going to be the inert version. Can we remember there's 2 examples for inert electrodes that I gave yesterday?
Platinum and carbon.
Yeah, so this one uses the platinum electrodes in it. Now, in terms of our electrolyte is water, but in this you have to add in sulfuric acid, and the reason you do that is because it improves your conductivity. It makes the electricity flow better. Okay, it won't let me finish conductivity. Okay, so what's our spectator ions going to be, do you think, here? So we're making hydrogen and oxygen.
SO4 2 minus.
Yeah, so SO4 2 minus again. So there's not enough energy in your system to be able to make SO4 2- react. Okay, so I'll go as far as here. So we're going to draw our triangle again. We are going to draw our little diagram in here. So you're drawing two little funky, I'm going to change that. So you're drawing essentially two burettes that are upside down, but these guys are linked together. Okay, we are going to connect it to our power pack. So we're going to put our anode on this side, so we'll try to keep the anode on the same side every time, and the cathode over here. And we put our little taps on the end, and we will have roughly twice as much. So this is going to be our hydrogen gas. This is going to be our oxygen gas. These are platinum electrodes. So what we see is going to be at the anode, gas produced, and at the cathode we have double the gas produced. So our explanation or our reason. So at the anode, water is oxidized. Now, you guys actually come preloaded with information because you, for my biologists, you've done both photosynthesis and respiration, and you have actually done oxidation of water in context of both things. So can you remember when you do something with water and you make oxygen in photosynthesis and respiration? Can you remember what that equation is?
Is it H2O plus energy gives protons,
Yep.
electrons, and oxygen?
It is. Good job. So it is H plus a half O2 plus 2 electrons. So this comes from photosynthesis respiration. So water is oxidized to protons and oxygen. And then at your cathode, water is going to be reduced. And this one is the slightly harder one, but straight away you know that you're making hydrogen. So that's okay. So we'll start writing our equation. So we have H2O. We are going to be adding our 2 electrons in. We know we've made hydrogen. I'm going to put 2 here. What elements are left now? Isn't that right? It is right. Oh no, no, ignore me. I'm thinking of something else. So, ignore me, I apologize for the emotional scarring. Okay, so water is oxidized to protons, and it's actually the protons that are reduced. I am thinking of the sulfate. So protons are reduced to hydrogen. So our cathode is going to be 2H plus 2E minus to give you H2. I think that's... So I'm going to highlight this. No, this doesn't give me a really thick one. Go with the orange. Okay, I'm going to highlight this because we're going to see this again in a different electrolysis.
Miss.
Yeah.
No, it's kind of hard to see on the screen.
Okay, well, I will put it in a blue box. So it's kind of easy to figure out that oxygen is made at the anode because it's oxidation. So anox, those two things are going to be linked. So if it's oxygen at the anode, it's hydrogen at the cathode.
What's the electrolyte again?
So the electrolyte for this one is water, but it has sulfuric acid in it. So we add sulfuric in it because that helps conductivity. So it is technically water, but there's sulfuric in there. Ready to see the third one?
On this one, is the H plus that's being reduced at the cathode, like, is the H2O oxidized at the anode and then that H plus is reduced to hydrogen at the cathode?
Yeah, so I'm going to change just how we present it. So obviously you could do it with platinum electrodes in your water. You can do it like this, but then you're not collecting your hydrogen or your oxygen. So this is our long line, this is our short line. So what you are doing here, as well as having the oxygen bubbles leaving, you will be making H plus. That's going to now be in solution, and that H plus is going to be attracted to your cathode. And once it's attracted to the cathode, remember now, in our electrolyte, it's the ions that are carrying the charge from yesterday, but actually up here, it is electrons that are being moved. So there will be electrons available for that H plus, because this is a complete circuit in terms of movement of current. It's a full circuit. But in the electrolyte, it's the ions in solution that provide the current, and in the wires and in the platinum, it's electrons that are in the metal that's doing the conduction that are present.
Right, thank you.
Does that answer your question? Okay, so we go on to the third one. So these two are weird, a little bit weird, because they kind of, the spectator ions now can play a part in this. So I need to change my share, new share, and we go to this. I think it's this one. So we're now looking at electrolysis of potassium iodide in water. And in this, we put phenolphthalein into this solution. So can you remember what color phenolphthalein goes if you have acid or base from the titration? So we put acid in our attic when we do our titration, and when we do phenolphthalein, what's the color change?
Pink to colorless.
It's pink to colorless. So keep bearing that in mind now. I don't know, does this have music? Yeah, he only has music. So they are using pencil lead here. They're using graphite. So the left pencil with the yellow is the anode, and the pink pencil is the cathode. So what might you know that's yellow-orange? Bearing in mind we have potassium iodide in there and water. Okay, so then the other question would be, what are we producing at the cathode that would make this pink?
An acid?
So think back to the titration for phenolphthalein. We put acid in the attic, we put base in the basement. the color change. What's the color change for that titration? So the color change is pink in the base to colorless in the acid. So we are making base here in this. Still no takers on what I could be making that's red, orangey from potassium iodide and water.
Iodine.
You're making iodine. So the brown color here is to give you the hint that you're making iodine. So we're going to go to here and we will go to here. Okay, so in this one, the good part is you get to see the colors, and that can help you figure out your products. So in terms of our electrodes here, they can be anything. They can be platinum. I don't know why this won't let me write. Okay, so the electrodes here could be platinum or they could be carbon. So you can actually do it with the pencil leads. You can't see the screen still. Now you can see the screen. Okay, so our electrolyte is Ki, but it's in H2O. So we have all of these ions in there. And in this one, our spectator is going to be the K+, because there's not enough energy to make that get involved. Okay, I'm going to draw this small, you'll draw it bigger. So in terms of our diagram, big line, small line. They're very far apart, so apologies, they should be closer together. So we have big line, we have small line, we have our electrodes coming down. We have our Ki in water, and we have the phenolphthalein. Okay, so at this side, I'm going to make it slightly brown. You will start to see, okay, I did pick brown. It's telling me I picked rainbow. Go with brown. So here you will start to see brown, and we will also get bubbles. Am I right on this side? No. Okay, so we get the brown on this side. On this side we will get pink, and we will definitely get bubbles. I'm right on that. Yeah. So what we see, do not know why it won't let me write. So what we see, so at our anode we see the formation of brown solution, and at our cathode we see pink solution plus gas bubbles. So our reason, so at the anode we said what is being produced. What's the brown?
Iodine.
Iodine. So we'll just actually label these. So this is platinum. This is going to be iodine. Formed here we're going to get base, and we are going to get hydrogen bubbles. So at the anode, iodide, I minus, is oxidized to iodine. And at our cathode, it is water is reduced to hydrogen and OH minus ions. just going to move this up a little bit. So for our half equations, then you should be able to write a half equation for I minus becomes iodine. It's going from -1 to 0, which is +1 electron. But I have to bear in mind I have 2 I's, so I have to double my I's here, and I have 2 electrons here. And then we're reducing water, so the water is getting the 2 electrons. So it is going to make me OH minus H2. So I need to make this 2, I do. And this equation we will see again in our last one. So for this one, you've got to know your color changes, and that'll help you with what's being produced. Okay, we're not going to get the last. Yeah, go for it, Lucy.
Is that a 2 before the OH minus?
Yeah,
The last line?
it is. So it's 2H2O plus 2 electrons becomes hydrogen plus 2 OH minus.
And that's at the cathode, is it?
That is at the cathode, yep. Sorry. So I will, for Wednesday, there's one more, and the one more uses the products or the things in the 2 boxes that we've just done. So it's oxidation of water and it's reduction of water, and there's colors that go with it. So I'll make the video, and there's just a tiny little bit then on electroplating, and that's going to be it. So there were the questions that I gave out. You should be able to start going through them now. Still won't be able to finish them. I'll try make the video today, and I'll put it up, and then you can get it done whenever you want. Okay, on Friday I will send you out, because hopefully we will know more, but on Friday I will send you out our revision timetable. And at the moment the revision timetable is making the assumption that there are no mocks. That's my assumption. It's not anyone else's. I've just made it on the basis that there is no mocks, and if we have to change it, we have to change it. Okay, we still have practical and stuff that we have to do. Like, we'll have to demo these. Okay?
Yes.
Yeah.
You know, in the last equation, is it H2 plus 2 OH minus?
It is 2H2O plus 2 electrons becomes hydrogen gas plus 2 OH minus.
Yeah, thanks.
Okay.
What are the spectator ions for this one?
So the spectator ions is the potassium K+, because they don't get involved.
Thank you.
Welcome.